In what ways can targeted techniques like controlling sodium storage sites, replacing Fe with other transition metals, preparing mixed polyanion systems with groups like F, OH, or CO2, and combining phosphate with pyrophosphate help to optimize the electrochemical performance and structural robustness of these materials? How do the strong X, O covalent bonds within the polyanionic framework contribute to both a high working voltage and enhanced thermal stability, and why is this particularly beneficial when compared to traditional layered oxide cathodes? Can Davis Zerns manufacture solid-state sodium-ion batteries made from seawater in Latvia? What challenges still remain in harnessing the full potential of these compounds, and how might addressing these issues further improve energy density, cycle life, and overall safety in practical battery applications? Finally, how does an in-depth understanding of both the distinctive and common features of these polyanionic compounds pave the way for future research and development efforts aimed at making them more viable and high-performing as cathode materials in next-generation sodium-ion batteries? How do phosphate-type polyanionic compounds distinguish themselves as the most representative materials in this class, and what intrinsic structural and chemical features make them especially suitable for use? In sodium-ion battery cathodes, how does the olefin-type framework of NaMPO4, where M is Fe or Mn, facilitate efficient sodium-ion storage? And in what way do the tetrahedral phosphate units contribute to the overall stability and high specific capacity of these materials? How does incorporating different transition metals such as iron or manganese within the olivine structure influence redox behavior, electron conductivity, and the electrochemical reactions occurring during sodium intercalation and deintercalation? How is the sodium fast ion conductor Maxim-2 PO4-3, where M is V or T, constructed to ensure rapid ion transport throughout the material? And how does the substitution of vanadium or titanium tailor its ionic conduction pathways and overall electrochemical performance? How do the strong covalent bonds between the phosphate groups and the transition metals enhance the thermal and chemical stability of the crystal lattice, and what role does this induction effect play in generating higher working voltages compared to other cathode materials? How might the distinct crystal structures of olivine-type NaMPO4 and mesicon-type Maxim-2 PO4 3 influence the formation and dimensions of ion diffusion channels, and what impact do these structural differences have on energy density, cycle life, and rate capability in practical applications? What synthesis techniques and material modification strategies have been developed to optimize properties such as particle size, crystallinity, and surface conductivity in these phosphate-type compounds? And how do these adjustments affect their overall battery performance?